All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let's actually jump into it. Screen broadcast. Screen broadcast. Okay. Cool. Can see the chat. I can see you guys. All right. Announcements before we begin. We do not have class on Friday because it is Good Friday. It is Good Friday. You don't have to wake up early. So yeah, so you won't have class with me or anyone else. This was also in the calendar that's in the syllabus as well as the academic calendar. Group projects will be posted on the class website a little bit after class, and we will otherwise at the moment not discuss groups because we have a lot to cover today, and I didn't even cover as much as I wanted to in the last class, so we're definitely not going to do that in this class. In terms of the group projects, I did reach out to someone in the business school who helped me gather some senior upperclassmen mentors for you. I don't know where they're all from. I know the original plan was to find you guys some MBA students, seasoned people who have been down your road before, but I honestly don't know. I'm actually meeting them on Thursday, I think. So I'll know at that point. But I would say coming up with a common meeting time is going to be important. So you should probably be on the lookout for doodle polls or something from me during this week, just to try to get everyone's schedule on board. So just want to make sure you guys look out for that. And of course, during the week, if you want to email me about the project, or I would say ask on the forum, we can do that. That being said, we are going to move on. I want to start by reviewing the counting principles that I already went over with you guys, just a quick little summary of what we did. And then I'll actually do some examples for you. And then I will leave you guys as some examples to do as well. So let's actually just jump into it. So review of what we did literally yesterday. Review of general accounting principles. Yeah. Okay. So what have we spoken about? Well, one, there was a rule called the multiplication rule. There are several ways to conceptualize this, but probably the nicer way for us and our applications would be to think of it as counting the number of possible total experiments that can happen if you know how many ways each stage of that experiment can happen. So this basically says if we have an experiment with our stages where Ni is the number of ways possible outcomes for stage I, where our I goes from 1 up to R, then so what we have is like boom, 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 dot, 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 boom, boom. So you have N1 options for the first stage, N2 options for the second stage, N3 options for the third stage, so on, going all the way up to NR options. So these are the stages. there are of them, and we know how many ways that each one can go, so these are the options, right? Then the total number of possible outcomes for the experiment is n1 times n2 times n3 times nr. Right? That's the total number of ways that this can occur. This point, I'm going to call this equation A, or expression A. Okay. Now, if all stages have the same number of possible outcomes, say each ni equals just n, they can happen in n ways, then the number of possible outcomes is, well, n to the r, but it falls by the same rule above. You just multiply n by itself r times. This is expression B. Okay, so those are the things that can come up. So another way you can think of it, the above can also be thought of as the number of ways to create tuples of size r with no restriction if A, each coordinate can take, let me say takes, each coordinate takes elements from a potentially different set to the other coordinates. Or B, each coordinate is filled in with elements from the same set. And the set has size n, right? So those are the two ways. You want to create a coordinate. If what you would put in each coordinate comes from a different set, the first equation would tell you how many possible coordinates you can create. If what you put in each coordinate comes from the same set with no restriction, you can repeat or whatever you can want to do, then the second expression gives you the number of possible tuples you can create. Okay. Now, we would want to also talk about counting with restriction. So, and that typically means no repeats. Like if we don't want to repeat something. If we want to kind of model the situation where it's in the real world, if we choose something and move it over here, then it's not over here anymore. You can't pick it again, right? So if you want to model that situation, we looked at two counting principles for that situation. And the first one is when order matters. And in that situation, we looked at two main numbers. We looked at one number, but there are two varieties to it. So one of them is PNR, right? So this was called a permutation, and it's the number of ways to choose things and put them in order. So this was n factorial over n minus r factorial. It was called a permutation. And it is the number of ways to choose R objects from N objects in a certain order or to be arranged in a certain order. Okay. And repetition not allowed. Okay, so that's very important in this situation. So I want to pick some things, put them in order, right? I have a pile of books over there. I want to take something from the pile of books, line them up on a shelf. It's going to be, there's an order to how I line them up on the shelf. There's the leftmost book, and then the book beside it, and the book beside that, and the book beside that. Or I want to have a group of people, want to pick people to be a president, a vice president, or a treasurer. There's an inherent order. I would use this number to figure out how many ways I can do that. So that's what that counts. Now, there was a special case of this number, which gave rise to the concept of the factorial. Come on, iPad. And it's when we choose all n elements. This ended up being n factorial. You'll also notice here that if I set r equals n in the previous equation, I would get 0 factorial in the denominator, which is another reason why it actually makes a lot of sense that 0 factorial is 1 from a formula standpoint. So this is called n factorial. And that is simply the number of ways to arrange n objects in order. In some particular order. Again, repetition not allowed. So, and this is something, and just as a general admonition, I suppose, like these things are important for you to pay attention to. An issue with, and I might go through and regrade these, but that's not going to happen until maybe the end of this week. But an issue that I saw with the test, for example, was that several of you didn't know which formula applied to which situation. So there was a problem in which you might need the sinking fund formula, but instead you chose the amortization formula, or vice versa, or something else. So it's actually important that you know when certain formulas apply to which situations. So it might not seem like math to you, but knowing these words is important. Like knowing when the formula applies is important, right? You should know all this. So definitely you want to pay attention to this. You want to write it down. You want to study this as well as the formulas, right? So those were the two main numbers introduced in the second counting session. then we had the case where 3 order does not matter. Anarchist. Okay, no. Order does not matter. Right. I can probably actually say something about this as well. The above, like the permutations here, can be visualized spatially as creating tuples where you are not allowed tuples from a set A where you are not allowed to choose the same element twice. Okay. So you can think of it that way. So there are times when, if you know this is the sort of idea you want to put things in order, you want to not count repeats, then when you think of permutation, what you can do is you can imagine that what you're doing is creating a coordinate. And really you just want to count how many possible coordinates can be created by whatever manner you want to create the coordinates with. In the case that order doesn't matter, we introduced something called a combination. So this was CNR, which was n factorial over r factorial times n minus r factorial. There was a notation that I didn't introduce last time that I want to introduce now, and it's n choose r. Notation Jhevon forgot to introduce last time. Right. So you just write parentheses and you write the n on top and the r on the bottom. You don't put a slash. There's no division. It's not a division sign or anything, but it's like a little vertical set of parentheses, and you put the numbers on top. And we'll see examples of this pretty soon. But that is what's called a combination. This is referred to as n choose r, or it's called a combination. But most people read it as n choose r. And it is the number of ways to choose r objects from n objects. In no particular order. Again, repetition not allowed. Okay. So in the previous examples, that would be something like, I have a pile of books over there. I want to pick a random subset of books and then just throw them in a pile over there. There's no inherent order to me creating the other pile. So how many ways can I do that would be a combination. It would not be a permutation. If I decide to line up the books on a shelf, now it's a permutation because the order matters. There's a way I can arrange the things on a shelf. There's no particular order to another pile, right? So depending on the situation, if someone asks you, oh, I have a pile, I want to take stuff from that pile to create another pile, you know that you choose combination. If someone says, oh, I have a pile, I want to take stuff from that pile to arrange on this in this way, then you know you choose a permutation, depending on the situation, okay? And of course, the way that has order, there will be more ways. Because once you have a pile, it's just a pile. However, once I have a certain set of books lined up on a shelf, then if I rearrange those books on a shelf, the same set of books can account for multiple rearrangements. So the permutation is always going to be the larger number. And of course, you can actually see that here because you're dividing by something extra, right? The permutation is what you would have without the r factorial in the denominator. So you can clearly see that it would be a larger number anyway. But it depends on the situation. Or there are 10 people over there. How many ways can I randomly choose 3 people just to randomly choose them and have them sit around a round table where no one has any certain title or authority over the other person? There's no inherent order. Then you'd use a combination. Okay. So we had that. Anything I'm forgetting here? Okay. I do want to mention something here as well. Just a little thing. I mean, you won't have to move your notes a lot, I don't think. Let me create a little bit more space. So I just want to remind you that we take the convention when it comes to permutations, that 0 factorial is 1. And I mentioned that verbally, but I forgot to write it down. Because if I set n equals r in the formula on the left, you get 0 factorial in the denominator, which if that's supposed to be equal to n factorial, the denominator would have to be 1. One of many reasons why 0 factorial has to be 1. It doesn't really make sense with the definition of factorial. Otherwise, it's just something that we make as a convention. We make up the rule. It's like how we make up all the rules of math, really. What else do I want to say? The above as in n choose r, can be visualized spatially as if we are creating subsets of a particular size of, let me just be a little bit more specific, because in terms of the numbers, we can be subsets of size r from a set of size n, right? So when it comes to permutation and order, we like tuples. You can think of these numbers counting the number of possible tuples that can be created, where repetition is not allowed. The combination, it's like if I have a set and I'm creating all possible subsets of a certain size from that set. And of course, in a set, repetition is automatically not allowed and order automatically does not matter. So I don't really have to state those extra here. I will say that's all that we actually talk about, and it's all we actually need for this. I will say though, in general, the above can be mixed and matched to solve a problem. In particular, mixing 1 and 2 or 1 and 3 is not strange or uncommon. However, chances are 2 and 3 will not mix. it would be very strange to mix 2 and 3 in the same problem, especially in the same stage of the problem. Right? Because if you are considering permutations, what you're saying is order matters. And if you're considering combinations, what you're saying is order does not matter. So for you to set up a problem where in the same breath you're talking about order matters, order does not matter, it doesn't really make sense. And I mean, it'll be very strange to mix 2 and 3. So what I'm saying is chances are you're wrong here. And I phrase it this way because I can't really think of a situation where you would mix these two, but I don't really want to say there's no situation where you would mix these two because, you know, like blanket statements like that often get people in trouble. But yeah, I can't think of a situation where you'd use both of these concepts in the same problem, especially at the same time. It's very strange. Especially permutations are going to be larger than combinations in general. So if you're using both, chances are your permutations are going to be too large relative to your combinations. And so if you're creating fractions with them, it's going to cause trouble. Something that I occasionally see students do is that they will use both ways in the same problem and they end up in trouble because of that. So we saw that probability comes down to you counting two things. You have to count the total number of possibilities in a certain set, and that goes in the denominator. Then you'd count the total possibilities in some subset of that set, which goes in the numerator. And I've seen students use different things to count different parts. So they'll use like a combination to count the denominator, but then use permutations in the numerator. It doesn't make sense. Chances are you're going to be wrong, almost certainly. Chances are your top is going to be larger than your bottom and you get a probability of larger than 1, which doesn't make any sense, or something like that. So yeah, make sure you don't mix combinations and permutations. We have some examples to go through, but there are some things I want to talk about first. Apart from that, one word, apart from this, the challenge is to know when to use which concept in some application. So not every time am I going to shout to you, oh, order matters, so do this. But you have to conceptualize the problem as, you know what, order is going to matter here, or order is not going to matter here, I don't care. So you have to choose, am I going with combinations or permutations? And then you might need to use the multiplication rule while using these. But that's going to be important. And we'll talk about that more when we get to probability. Let's start off from last time, because I need to make sure that you guys actually know how to compute these things. I asked you guys to find C of 25,7, which now you know can be written as 25, choose 7. I also asked you to find P of 34, choose 9. I shouldn't use the word choose there, but and maybe just to compare, C of 34, choose 9. So I want to make sure that you guys know how to do this in your calculator. It'll be very important. So what did you get for the first one? C of 25, choose 7. If you didn't do it, I'll give you a couple minutes to do it now. It's very important that you know how to do this in your calculator.
Wait, when you do it in your calculator, do you do the 25 first and then the C and then the 7? Is that the order?
It depends on the calculator, but usually yes.
Okay, I got 480,700.
I believe that's correct. And you're using a TI-89?
Yeah. Or TA4.
You're right. So you would enter the 25, you would go to the menu, math probability, you would choose the NCR, then you would enter the 9, the 7. Yeah. What about the P34 9, 34 P9? By the way, this is equal to number of ways to choose 7 objects from 25 objects. You wouldn't want to actually do that by hand. Count up to 408,000 different combinations. P of 34 9 or 34 P9, what is that one?
I think mine's very wrong, but I got like 1.9 and then E13 on my calculator.
1.9 times 10 to the 13?
Yeah.
Yeah, it's possible. It's huge for sure. Does anyone have all the numbers? Because I believe it was something like 19,033,511,777,280. So yeah, it was a lot. Right, so it's 10 to the 13. Huge number. That is the number of ways to choose 9 objects from 34 objects in a particular order. What about C of 34, choose 9? Go. More practice you get, the better here. Because on the next test, you're going to have to be using these calculations multiple times. You definitely want to get comfortable in writing these out, doing these in your calculator.
For this one, I got 52,451,256.
52,451,256.
256, yeah.
Yeah, I think that's right. Notice how much smaller than P of 34 choose 9 that is. Right? They're not the same magnitude. Right? If you're using the permutation and the combination in the same problem, chances are you're going to get an incorrect number because the permutation is so overwhelming compared to the combination. It's not even funny. Like 19 trillion compared to 52 million. That's like a huge. It's like very huge. So yeah, and this one is no order, whereas the order, you can have multiple rearrangement for the same 9 things that are chosen, right? I did also want to show you guys that if all else fails and you can't really use your calculator very well, you could use Wolfram. And you can actually type the notation as I gave you guys. So for example, we can do the 34C9. And you'll notice that, yeah. So there's that new notation that I spoke about. These guys are also called binomial coefficients. That's because they're used in the binomial theorem. You can figure out the rows of Pascal's triangle. We're not going to talk about that, but whatever. But you can see right here, 52, 451, 256, 52 million. And 30, that's 34, choose 9. You can also actually type, you can type out that phrase, 34, choose 9. And it'll understand it as the same thing. Of course, if you're multiplying these guys together with something, you'd need to put parentheses. So 34 choose 9 times 23 choose 2. And so you can do something like that. And you can get an answer that way as well. Yeah, so just wanted to show you guys that you can do it in Wolfram as well. For the permutation, you can do, what did we have? 34 P9. You'll see that here. Yeah, it's 1.9 times 10 to the 13, or it's going to be, 19 trillion, 33 billion, 511,777,280. Yeah, so that's cool. All right, let's go back. Now what I want to do is some examples. So I'm going to take one for the team. I'm going to do the hardest in these set of examples. I'm going to do the first 3. I'll leave the rest to you guys after I put you guys in your groups. So I would say something like, two, three, four, five. Yeah, so something like, and we'll pick up with this next time, group 1, which I'll tell you guys later, should do problem 4, group 2, problem 5, group 1, problem 6, group 2, problem 7, and all groups try problem 8. So try these at some point over the weekend and let me know what you guys get on Tuesday. So each group can work on 3 problems. But let's actually continue with me doing some of these problems for you. So okay, so here's a scenario. Counting is important, probably. We've already been through that. Let's just actually get into the mood of counting. You have 3 shirts and 2 pants. Let's pretend. How many possible outfits can you create? Here's the thing we can think of creating an outfit. As an experiment. Yeah, the way some people dress, right? It's an experiment. As an experiment with 2 stages. So of course, the first stage is, say, to choose the shirt you're going to wear. Second stage, choose pants you're going to wear, right? You would have 3 choices here. You would have 2 choices here. And the multiplication rule says you would have 3 times 2 equals 6 total possible outfits. Okay, so that's using multiplication rule. Okay, so hopefully that's clear. Yeah. It's one of the harder problems in this set, man. You toss a fair coin 3 times. How many possible outcomes are there? Again, we can think of tossing a coin 3 times as an experiment that we want to know what the outcome is going to be with 3 stages. The stages here being the toss. So stage 1, stage 2, stage 3. So this is toss 1, toss 2, toss 3. I know there are 2 options here, right? That could be heads or tails. There's 2 options here as well. Another heads or tails, 2 options here. So by the multiplication rule, we have 2 cubed equals 8 total possible outcomes. There are 8 ways that this can go. The multiplication rule. Okay, so there's that. That's 8. By the way, all these problems, they'll be posted in the notes, of course, where you usually find them, but they're also posted in a PDF on the class webpage. I think if you scroll to the bottom, you'll see a document labeled counting examples, and I copy these examples from there. So you toss 2 fair 6-sided dice. Right, so a dice is, you know, that little cube thing with the numbers on it, Casino Royale. Right. Again, experiment with 2 stages. Outcome of die 1. Outcome of die 2. Right. So in a fair 6-sided die, there are 6 possible outcomes. Here, there are also 6. That tells you this is 6 squared. This is equal to 36. Total possibilities. Total possibilities. Especially if order matters, that would be total 36 total possibilities. There's a nice way to visualize this. Could be a 6-sided dice, could be something else, but you can actually create like a table where, you know, the outcome of die 1 is across the top column, 1, 2, 3, 4, 5, 6. The outcome of die 2 is going down the rows, 1, 2, 3, 4, 5, 6. Right, so you have these stages here. And you can actually visualize it. Like if I go say row to column and write it as a coordinate, put it in this table, I would have, say, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Right? And sometimes you want to visualize things like this because you can talk about certain situations. So I can say something like, oh, how many ways can the both dies have the same output? It's easy to see here, that's 6 ways. Or how many ways can you get the sum to be 4 going down this diagonal? How many ways can the sum be 7 going down this diagonal, right? You'd be able to see a lot of situations very clearly, very visually. So what I want to do now is just put you in your groups for a couple minutes and then let you go. You won't have to come back to the room, but that's going to be that. Hopefully you guys can work together to come up with these examples, can use it as a group, a team building exercise to kind of come up with these. But yeah, that's what we are going to do now. So that's the end. I'll put you guys in your groups and you guys can get each other's contact information and just kind of try to set things up from there. So I'm going to end the recording here because you're not going to come back. So I'll just say my goodbyes and then I put you in your groups. So I guess, hey, I'll see you guys in the next one. Ciao. Okay.